Welcome. Today, we'll explore two fascinating types of hydraulic structures, arch dams and buttress dams. These dams play a crucial role in water management, power generation, and flood control. While both are designed to hold back large volumes of water, their structural principles, design considerations, and applications differ significantly. In this video, we'll break down the definitions, types, design methods, and key differences between arch and buttress dams, helping you understand when and why each type is used. Let's start by understanding what makes these dams unique. Arch dam is a solid wall, typically made of concrete, that is curved in plan and spans the entire width of a river valley. Its unique curved design allows it to transfer much of the water load horizontally to the strong, rocky canyon walls, reducing the thickness needed compared to gravity dams. This efficient load distribution is the primary advantage of arch dams. The greater the curvature, the more load is transferred to the abutments, resulting in a thinner, more economical structure. However, constructing an arch dam requires strong, stable foundations and advanced engineering skills. Arch dams come in several types, each with unique design characteristics. The main types include constant radius arch dams, variable radius arch dams, and constant angle arch dams. There are also double curvature or shell arch dams, which are curved in both plan and section, making them highly efficient but complex to design and build. The choice of type depends on the valley shape, foundation conditions, and economic considerations. For example, constant radius dams are simpler but use more concrete, while shell arch dams are thinner and more economical for tall structures. Constant radius arch dam features a curved surface where the radius remains the same at all elevations from top to bottom. The centers of these arcs lie on a single vertical line, making the design straightforward. However, the thickness of the dam increases towards the base to withstand higher water pressure. This type is sometimes called a constant center arch dam. While easy to design and construct, it uses more concrete than other types, making it less economical for very tall dams. Variable radius arch dams have radii that change with elevation, being largest at the top and smallest at the bottom. This allows for greater efficiency, as the dam can be thinner where the water pressure is lower and thicker where it is higher. The centers of the arcs do not align vertically, making the design more complex but more economical in terms of concrete usage. These dams are especially suitable for V-shaped valleys, where the width changes significantly with height. Constant angle arch dams maintain the same central angle for the arch rings at all elevations. This design is highly economical, as it allows the use of the best central angle for minimizing concrete volume. However, achieving this often requires overhangs at the abutments, which in turn demand very strong foundations. While more complex to build, constant angle arch dams are preferred when maximum material efficiency is needed and site conditions permit. Double curvature or shell arch dams are curved both in plan and in section, forming a shell-like structure. This three-dimensional design allows for extremely thin dam sections, making them the most economical in terms of concrete usage. However, the design and construction are highly complex, requiring advanced engineering knowledge and precise construction techniques. Examples include the Vajont Dam in Italy and the Idukki Dam in India, both known for their slender profiles and impressive heights. Some of the world's most famous arch dams showcase the advantages of these designs. The Hoover Dam in the USA is a constant radius arch dam, notable for its massive base thickness. In contrast, the Vajont Dam in Italy and the Idukki Dam in India are double curvature dams, achieving remarkable heights with much thinner bases. These examples highlight how the choice of arch dam type can dramatically affect material usage and structural efficiency. Arch dams are subjected to several forces, including water pressure, uplift pressure, earthquake forces, silt pressure, wave pressure, and ice pressure. However, the relative importance of these forces differs from gravity dams. For example, uplift pressure is usually small and often neglected due to the narrow base. On the other hand, stresses from ice, temperature changes, and abutment movement are more significant and must be carefully considered during design. There are three main methods for designing arch dams: the thin cylinder theory, the theory of elastic arches, and the trial load method. The thin cylinder theory is used for preliminary designs and assumes the dam acts as a thin shell, but it has limitations, such as ignoring temperature and abutment effects. The elastic theory accounts for additional stresses like temperature changes, shrinkage, and abutment yield, providing a more accurate analysis. The trial load method is also used for complex cases. Key concept in arch dam design is the best central angle. This is the angle at the center of the arch ring that results in the minimum volume of concrete required. Through mathematical analysis, it has been found that the most economical central angle is approximately 133 degrees 34. While this angle can only be achieved at one elevation in a constant radius dam, It serves as a target for optimizing material use in more advanced designs. While the thin cylinder theory is useful for initial design, it has several limitations. It assumes the arch sections are thin and free at the abutments, which is not the case in reality. The theory does not account for shear and bending stresses, temperature effects, ice pressure, or abutment yield. It also ignores the plastic flow and shrinkage of concrete. For precise design, more comprehensive methods like the elastic theory are necessary. Elastic theory considers additional stresses that affect arch dams, such as temperature changes, shrinkage, abutment yield, and rib shortening. These factors can significantly influence the dam's structural behavior. For example, temperature changes can cause the dam to move upstream or downstream, while abutment yield increases the span and induces extra stresses. The elastic theory provides formulas to account for these effects, leading to safer and more reliable design. Buttress dam is an innovative structure designed to save concrete by using a series of solid walls, or buttresses, to support a relatively thin upstream face. Instead of a massive solid wall, buttress dams use these supports at intervals, reducing the amount of unstressed concrete. The upstream face can be a slab, arch, or even a dome, depending on the dam type. This design is especially useful where concrete is expensive or foundation conditions are less ideal for a solid gravity dam. There are several types of buttress dams, each with unique features. The most common are the deck slab type and the multiple arch type. Deck slab buttress dams use a reinforced concrete slab supported by buttresses, suitable for smaller heights. Multiple arch buttress dams use a series of arches supported by buttresses, ideal for taller structures. Other types include the multiple dome type, massive head type, and columnar buttress type, each offering specific advantages depending on site conditions and design requirements. Deck slab buttress dams feature a reinforced concrete slab inclined to the horizontal, supported by buttresses spaced at regular intervals. The slab is designed to carry both the water load and its own weight, providing stability against sliding. These dams are generally used for heights up to 50 meters. The design involves optimizing the spacing and thickness of the buttresses to minimize concrete use while ensuring safety and stability. Multiple arch buttress dams use a series of arches on the upstream face, each supported by buttresses. This design is preferred for taller dams, as the arches efficiently transfer loads to the buttresses and foundations. The stability of each unit depends on adjacent units, so good foundation conditions are essential. Examples include the Manicouagan 5 Dam in Canada, which stands at 210 meters high. The spacing of buttresses can be larger in this type, making it suitable for wide valleys. Beyond the main types, there are several specialized buttress dam designs. The multiple dome type replaces arches with domes, allowing for even wider buttress spacing, but requiring very stable foundations. The massive head type enlarges the heads of the buttresses to form a continuous water-supporting surface, offering construction simplicity and increased resistance to sliding. The columnar type uses columns to support the deck, but is less common due to construction challenges and cost. Designing a buttress dam involves optimizing the spacing, height, and thickness of the buttresses and the upstream face. The most economical spacing depends on the dam height and the slope of the upstream face. Engineers use master curves to determine the best combination of these parameters for minimum concrete usage. The loading and safety criteria are similar to those for gravity dams, but the distribution of forces is different due to the presence of buttresses. Master curve is a graphical tool used to determine the absolute economic value of buttress spacing for a given dam height and upstream slope. By plotting concrete quantities against different slopes and spacings, engineers can identify the most efficient design. This approach ensures that the minimum amount of concrete is used without compromising safety or stability. Each project requires its own analysis to find the optimal values based on site-specific conditions. Summarize, arch dams and buttress dams are both innovative solutions for water retention, but they differ in structure, design complexity, and material efficiency. Arch dams rely on curved geometry and strong abutments to transfer loads, making them ideal for narrow, rocky valleys. Buttress dams use supporting walls to reduce concrete usage, making them suitable for wider valleys or where concrete is costly. The choice between them depends on site conditions, available materials, and required dam height. Understanding these differences helps engineers select the best dam type for each project.